Alright, I have your quiz up next to me, so everything I do is going to be based off of that. So let's start right away by asking whether or not we can add these. At first glance, you might think that we can't because the bases are different, but what you need to do is simplify first. And by simplify, I mean starting with the factor tree for each of them. So 12 has a factor tree of 6 and 2, which breaks down into 2 and 3. 75 has factor tree 25 and 3. This breaks down into 5 and 5. So now you can rewrite these as 2 squared times 3, and the 75 you can write as 5 squared times 3. Now, as you know, when the index is missing, it's because it's really a 2. And this lets you separate based on the notes that we have from section 6.2 or 6.1, I think, that you can go over and review. That you can split these up into the ones that can have exponents that can be divided by the index and ones that can't. So let's do that for both of them. So once we have it split, it's very obvious that this exponent up here can be divided by the index, so we'll just go ahead and do that. And once we do that, by the way, the radical goes away. And then the reject list, the ones that you can't do it for, just stay normal. That's why we put them there, because we can't reduce them or make the radical go away. So we do the same thing for the second root of 5 squared. We'll cancel the exponent with the index, and we'll just get 5 outside by itself, times the square root of 3. But notice how this is the same now. These are the same base, same index, and this falls into the case where we can add these two together, in which case we look at these coefficients. It's kind of like if we have 2 apples and 5 apples. Think of the square roots of 3 as the apples that we're adding together. If I have 2 of them and I add 5 of them, I should get a total of 7 of them. So that completes the answer for that one, and this is the most simplified that you can make this. So that's with an addition. Obviously, with a subtraction, supposing this was a subtraction in between, this would change the answer accordingly. You would get a negative 3 rather here instead. But for everyone else that's going to see these notes afterwards, I'm just going to leave it as the actual answer. 7 square roots of 3. Alright, so now let's talk about a multiplication. So I'm coming up with these as I go, so please bear with me. But these are just like what you're going to see on the test. So let's do something like the square root of 4x squared y times the square root of perhaps 9 xy cubed. So what you're going to want to do is unify these under the same square root, and I'm going to do that by multiplying these two things together that I'm putting in parentheses, and then putting their result underneath the same square root. So let's do that off to the side. Let's make that multiplication happen. So 4x squared y times 9xy cubed. You can break this down by multiplying the numbers together, multiplying the like variables with each other, and then you put your result together afterwards. I like to, put these little markers to denote that they go together. So 4 times 9 will give me 36. And then I guess if I maybe write lines to denote where their result is going to end up, x squared times x is x cubed. And finally, y times y cubed is y to the 4th. And so this is because, for instance, x squared times x, if you write this out, x squared means x times x. And so now that's just x squared. Now if I add in that extra x, I'm doing x times x times x. But this just means x cubed. So what we're essentially doing is just adding the exponents together. Another example is if I have y cubed times y to the 4th, just add the exponents to get y to the 7th. This is the same for division, where most of you are getting confused. If I have something, for instance, like y to the 7th divided by y to the 5th, it's just a subtraction of the top minus the bottom to get me just y squared. So whenever you're multiplying variables with exponents, you're either doing addition or subtraction, no multiplication, and no division. just addition and subtraction. So that's a little side note, but this is the result that we wanted. This should go here. And once you're at this step, you just fall back to what you're used to when it comes to simplifying radicals. You're now just simplifying this guy, which is the task that I'm going to undertake over here to the right. So the first thing that we want to do when we see numbers is, as you know, perform the factor tree. This will be a little bit redundant because we know that 36 comes from 4 and 9. So we're just going to undo our multiplication, but it's procedural. It'll always guarantee you for you to find the right answer this way, so just stick with it. You have 4 into 2 and 2, and 9 into 3 and 3. This you can recognize as 2 squared times 3 squared. And so we're going to replace 36 with that prime factorization. So we have the square root of 2 squared times 3 squared times x cubed times y to the 4th. Now when we're missing, again, the index, it's because it's really a 2. Now we do this splitting procedure where we basically take all of the parts of this whose exponents are divisible by the index. And divisible means goes evenly into when you divide. So readily you can identify that these two automatically fit because their exponents are divisible by the index. Same with the y. But this is a problem. We have an x3 for which that's not true, but we can solve that. Because we know our multiplication of variables leads to an addition, we know that x cubed can also be written as x squared times x. That's in fact exactly what we talked about over here. So what we can do is we can split x cubed into the x squared part and the x to the 1 part, because this exponent is now divisible by the index as all of these were, and that's what we want. So now let's do that. Let's split all these guys up into the group where their exponent is divisible by the index. So now x squared, this guy, comes with us. And then the group that doesn't, for which that's not true. So we have the x over here just by itself. X to the 1, by the way. This is the guy that we didn't want in that group of everybody who has exponents that can be divided by the index. And we'll just go ahead and do that. We'll do 2 divided by 2, which gives us 2 to the 1 outside of the radical. Once you do this division, the radical cancels. It goes away. So then, again, 2 divided by 2 just leaves us 3. Same here, just an x to the 1. I don't write the 1 whenever we have an exponent of 1. We just omit it. And then we do 4 divided by 2 to get us y squared. Now, this reject pile, we just leave it unresolved, unsimplified. That's why we put it on this side by itself. Now we just compute this this little multiplication to complete the solution to this problem. So that's that for this last problem that we were working on. So just to recap, we have this is a problem, and then oops, that is completely irrelevant. This is a problem in and of itself over here, and then this starts a new one right here. Alright, so let me just mark that off, and we'll begin another one, a division problem. And by the way, I'm going one by one based on what's on your quiz. It starts off with an addition problem, then it follows a multiplication problem, then it follows a division problem. So that's what I'm about to do now. So let's do something like this. The cube root of 32 x to the 4th y. Let's do something large, like 9. Divided by the cube root of something maybe like 4x, probably y, just y. That sounds fun. So now what we're going to do is the same thing that we did for the multiplication up here. Notice how I unified them under one radical. I performed the multiplication off to the side, and then I put that under the one radical. Let's just do that same thing. Let's set up that one radical with a cube root, by the way. That index is very important, carries over. And let's carry out the division off to the side. So this is a 4, don't be confused. This is divided by 4xy. And then again, we're just going to pair it off like we did for the multiplication. Numbers with numbers, variables with variables that are like each other, and so on and so forth. So it's very actually nice to do division because it's set up, it's almost aligned vertically. So we do the 32 divided by 4 to give us 8. And then x4 divided by x. Now here's what I was talking about. X to the 4th divided by x requires a subtraction of the exponent. So I'm doing a 4 minus the 1 that's not there. And when you do 4 minus 1, you should get 3. And that's our exponent answer. Same with the y variable. So you do y to the 9th divided by y is 9 minus 1. Because the 1 is invisible. Not there. It means it's 1. To get y to the 8th as your answer. So this result goes underneath there. And now again we come back to the case of where we're just simplifying this, which is something that we're used to and we can do. So I'll fall back to this part now where I'm doing the factor tree. So let's do the factor tree for 8. I know it's overkill because we've already seen this so many times, but just for those that aren't too familiar with the factor trees yet, it can be split up into 4 and 2, and this is because 4 times 2 is 8, and this can be split up into 2 and 2 because 2 times 2 is 4. That's where that comes from. It's not just willy-nilly. So now we put the result of that split, which is, by the way, 2 cubed, into the spot where 8 was, and so we have the cube root of 2 cubed x cubed y8. Alright, now we do the same thing that we did up there, but maybe just to reinforce it, we'll do it again thoroughly. So everything that has an exponent that's divisible by the index stays. These are 3's, these are good, so they stay. This is a problem though. Y to the 8th. That's not a multiple of 3. It's not divisible by 3. Because 8 divided by 3 apparently requires 2.66 something. That's not an even division. No bueno. So we need to split the y to the 8th into something that is divisible by 6 and something that isn't. And these two things here need to add up to 8. So we need to choose these so that they add up to 8, and we have the biggest multiple of 3 so that we get a number divisible by the index, which is 3 here. And that number, if you think hard enough, is 6. So naturally, what must be over here in order to equal 8 when you add them is 2. But this is the guy that we're looking for because now its exponent is divisible by the index and it fits into the crowd of cool people that we've been looking for. So now let's do this split. We're going to use it. We're going to write everything as the cool guys, now including y to the 6, and the rejects that we don't want, which is just y squared, so this guy. This is the cool guy, he goes with the cool kids, and then y squared is the reject, which goes with the rejects. So now we can just divide all of these exponents by the index here. That cancels the square root as soon as we do that. We get 2 to the 1, which I omit because whenever there's a 1 you don't write it. X to the 1 and y squared because 6 divided by 3 is 2. Then you're just keeping this reject off by himself because he's a stinky loser. And that would be your answer for this problem, for the division problem. So let's move on to something else. I might get some errors as we go through this because this tends to be buggy. So let's see how well we can go through with this. So as of right now, I think my other page is freezing, so just bear with me. I'm going to pause the video. Alright, so while I was waiting on the page to load, I went and got some food. So now I've got re-energized to keep going. The next thing, the next thing on your quiz is converting from exponential form to radical form. So, or rather the reverse. So let's start with that. Let me section this off really quickly. So you're doing, this is very simple. The next two problems are no-brainers. You shouldn't lose points here. So you're basically taking something like x plus 3 to the 3 halves, and recognizing that the denominator, let me change colors here to something more fancy. No, green's kind of lame. So the denominator here becomes the index of the radical that you're making. And then the numerator here becomes the exponent of the radical that you're making, and now you have all the ingredients to make it. This is the index that goes in the nook of that radical. And then of course the 3 is the exponent of whatever this exponent here is applying to. So I don't know if you caught that. I encourage you to rewind and see how that worked out, but it's very simple. It's just placing the numerator in a certain spot, whoop, and then the denominator in another spot, just like that. Let's try another example in case that wasn't clear enough. Let's do m to the 3 over 7. Now that was a 4. Let me just back up and do that again. Alright, come on. So 3 to the 7th. Very simply, you're going to grab, by the way, these are equal to each other. They're the same thing. Another way of writing the same thing. You're going to grab the denominator, put it in the index, and then the 3 is going to be the exponent. Very key observation here. I can put it as an exponent on the m inside of this radical, inside of the house, or I can have the radical with the m underneath and then put the exponent on the outside. They are equivalent. They are the same thing. So I can prove that actually really quickly. So if we're doing something like I don't know, the 8 to the 2/3, well, I can do what I've been telling you. I can put the 3 as the denominator as the index. Then I have 8 squared. I put the power inside of the radical. Well, let's compute that, see what we end up with. This is going to be the cube root of, let's see, 64, which we can break down into, you know what, this is ending up not too pretty and not too nice. You'll just have to take it for granted. These two things that I just described are the same thing. And you'll see that they become actually very useful. So for instance, if I'm computing something like, I don't know, 27 to the 2/3, well, I can write it as the cube root of 27 squared. This is a better example. I should have started with this. This is also equal to the cube root of 27, then afterwards squared. You see how the number is outside versus inside? Well, both would be the same thing. You know what? I think it'd be fun to pull up the calculator and show you that that's true. So let's do, let's see, edit, view, scientific, because we're scientists. Let's do 27 squared. For all you people that find this boring, you can skip it. This is not essential. I'm just proving why it's true. So you get 729. So here on the left, we're computing the square root, the cube root of 729. So now let's just compute the cube root of 729. Right there, it's already available for us. We get 9. And on the right, on the inside, we can immediately calculate the cube root of 27 in our heads. We don't even need this fancy schmancy calculator. We can do that in our heads to get just 3. So we get 3. And by the way, the squared is still on the outside. But then 3 squared is easy to compute. That's 9. So you notice on the right, we didn't really need a calculator. We could just do this in our heads, showing you that it's a lot easier when the exponent's on the outside in most cases. Because then we'd have to worry about cube rooting 729, which is, I don't think anybody finds that fun. So anyways, this is called converting. Alright, I don't know what is going on with you. Hold on a second. Let me see. This is not the right place for a caption, but the people viewing this afterwards are just going to have to deal with it. So this is called converting from exponent or exponent form to radical form. And then, as you guessed it, we're going to do the reverse. We're going to convert from radical form to exponent form. I'm wondering, as I do this, am I sounding interesting enough and fun to keep you engaged, or have you all fallen asleep? Well, I don't know how to, I want to keep this as professional as possible. I have a dream that perhaps one day a bunch of little boys and girls from all over the world will watch this video and learn how to do some of this stuff. But that might be just way too ambitious. So, for now, I'll keep it professional. And we'll move on to the next thing, which is the converting of basically the backwards way. I think if you can do the forwards way, you should be able to do the backwards way. So, let's take something like the fourth root of x plus 2 squared. And then again, we recognize that this was the denominator of the fraction, and then this was the numerator of the fraction. So then very quickly I can take the thing that's inside and form the the numerator and the denominator, which of course I can simplify to 1/2. So this video is already 21 minutes long. I'm sorry to have taken so much of your time. I'm going to try to breeze through the next sections. So let's see. I guess for those of you that gotten this far, I'll give you a nice treat. This is my personal email that I encourage you to write me with questions on stuff that you're still not familiar with. So please feel free to contact me about anything. School related, of course. So let's move on to the next thing, which is a multiplication. A binomial, it's one of the multiplications where you're going to have to FOIL. And it looks like this. The square root of x plus 2 square roots of 3. And then the square root of x minus, let's say, 3 square roots of 3. So I'm going to just FOIL, which means I'm going to multiply this times this times that, this times this, and then this times that. And I'm going to label these multiplications 1, 2, 3, and 4. So let's do 1. Multiplication 1 is saying take the square root of x and multiply it by the square root of x, which is, again, this is what we talked about in the beginning. Multiply the two things underneath, join them under one square root, you get square root of x squared. And of course, what's the index when it's missing? 2. So this is very easy because now you just divide the exponent by the index to get just x for number 1. Then 2. Multiplication 2 is asking for the square root of x times negative 3 root 3. So with this one, it's a little bit more complicated because you have this number out in front. All you got to do is multiply these two guys together and then tack on that negative 3 out in front afterwards. When you multiply those two guys together, so leaving the 3 out on the outside, you'll get 3x. Very simply, just 3 times x under 1 square root. It's the same unifying process that we talked about in the beginning. Alright, multiplication 3 says the 2 square roots of 3 times the square root of x. Again, keep this guy out in front and multiply the square root of 3 with square root of x by taking 3 times x and putting it under the same square root, kind of like we did up there. Then lastly, multiplication 4 is 2 square roots of 3 times negative 3 root 3. So you'll multiply the fronts together to get negative 6 and the radicals together to get the square root of 3 times 3, which is 9. But the square root of 9 is computable. You know that the square root of 9 is 3. So now you have negative 6 times 3, which is negative 18. Now you have all the ingredients to add together to form your answer. So you have 1, which is x, and now you're adding it to negative 3 root 3. So it's a negative, so you're just basically subtracting. And this is multiplication 2. And then you have the third one that you're adding is positive, so you're adding it. to square root of 3x, and then lastly you're adding the negative, so you're subtracting 18 for multiplication 4. But we're not done. We notice that these are like terms. So if I have 2 of these and I'm taking away 3 of these, I should have -1 of these left. But we don't write the 1, we just leave it without it. And then that is our answer. That is directly, exactly, very similar to something that's going to be on your test. So if you've followed along so far and you understand, you're going to be fine. In fact, take these as notes and use them tomorrow. Okay. Last 2 or 3 problems look like this. You're going to be asked to find the square root of x plus 4. Oh, I can keep this under 30 minutes. That's perfect. Although I just wasted time saying that. So, let's carry on. I have this radical, which, as you know, my first step is to isolate this radical. To do that, I want to get rid of this clingy 2 by doing the opposite of what's being done there, which is addition. So I want to add it to both sides. When I add it to both sides, it goes away there. And then I can do a 3 plus 2. Most of us know that to be 5. So I get this new equation. Now, to cancel the square root, you have to square both sides. What this means is you have to multiply the left side by itself and the right side by itself. Squaring, that's what that means. So, square here undoes the square root. They cancel each other. They undo each other like fire and ice, or like night and day, I guess. I don't know. When they cancel each other, you are just left with x plus 4. And on the right, we can compute 5 squared to be 25. Very easy. So, by the way, the parentheses are completely unnecessary, so we'll just get rid of those. And now we have a very simple equation that I'm sure you can solve. Just subtract both sides by 4 to get x equals 21. Okay. So, let's see. Let's try one where you have an exponent that's a fraction. So let's do maybe x plus 2 to the 3/5. I'd rather do one where you end up with a absolute value sign. So 2/5 is plus 3 is equal to, I don't know, 5. No, that's not good. Let's see, I want to do 1. No, that's not good. Bear with me, I got you, hold on. Let's see, I'm going to compute. So, 7, that'd be perfect. Alright, so we want to basically do the same thing, isolate this guy, that big parentheses with an exponent by subtracting 3 from both sides. And then we get x plus 2 to the 2/5 is supposed to be equal to 4. Now we raise both sides to the 5/2, which is the reciprocal of 2 5s. 2 over 5, the opposite of it, if you flip it, is 5/2. And that's what we want to raise both sides to, 5/2. When you do that, this cancels with this. But because we have a 2 in the fraction, we're going to have to use absolute values. This is in your notes. So when you cancel, everything is gone except it has absolute values. And the right, of course, you have to figure out. So to figure out the right, we write it in radical form. This denominator is the index. This numerator is the exponent. And again, we use that nice rule where we can put the exponent on the outside. You'll see why this is handy. Because now I can compute the square root of 4 in my head. Square root of 4 is just 2. So I'm doing 2 to the 5th. And as you know, 2 to the 5th is 32. So now I'm just solving x plus 2, x plus 2 absolute value equals 32. And as you know, I just make 2 equations to solve this. I do x plus 2 equals 32, the positive version. And and x plus 2 equals negative 32, the negative version. So it splits into these two equations, which you both solve. Subtract 2, standard stuff, equals 30. Subtract 2 to get negative 34. Two answers. Now, we're not done. I know we're at the 30-minute mark, but it'll only be like 2 minutes over. So the next thing that you have to do to see if they're both correct is check them both. You have to check both of them into the original. So the original was right here. X plus 2 to the blah blah blah, so on and so forth. So let's put 30 in. So we have 30 plus 2 to the 2/5, yes. And then we're supposed to be adding 3 to get 7. So this part, this is 32, and then I'm going to convert it to the radical form to be the 5th root of 32, all squared, plus 3 equals 7. And this is going to give me, let's see, the 5th root of 32, by the way, which we computed, because 2 to the 5 is 32, therefore the 5th root of 32 is 2. So 2 squared plus 3 equals 7. 4 plus 3 equals 7. 7 is equal to 7 last time I checked, so that's good news for us. Now let's try it with negative 34. Negative 34 plus 2, 2/5 plus 3 equals 7. So this is the 5th root of negative 32 squared plus 3 equals 7. This is negative 2. You can check that because if you raise negative 2 to the 5th, you'd get negative 32. You're supposed to square this and add 3, and you're supposed to get 7, but let's see what happens. When you do negative 2 squared, you get positive 4. Adding 3, that does give you 7. So it turns out that worked too. So these are your actual answers. Check and check. And I think, at 32 minutes, we should wrap this. Thank you for watching. Again, here is my email. That is superlaza7@gmail.com if you have any questions. Thanks for watching.